Microphone? Okay. Yeah, now it's working. So I will talk more about UEFI insecurity. So my name is Alexander Matrosov, and today I will present in Betraying the BIOS, going deeper in BIOS guard implementations. Actually, I'm very happy to present on first edition of OffensiveCon because my personal opinion, offensive is very important for make defensive stronger, and it was already very right points from the keynote speaker, Rodrigo Branco. And actually, I don't see any right path for development teams how they can make products stronger without offensive security team because actually, unfortunately, usual developers don't understand how the right implement the mitigations and security technologies and during security development lifecycle, somebody should break the things to make it right? Okay, so I'm leading embedded security at NVIDIA, and I have a lot of experience before in reverse engineering and security research. And actually, we dropped some stuff inside the book Rootkits and Bootkits, based mostly on legacy bootkits on MBR and VBR infections, but also have very interesting chapters about UEFI implants. Actually, this talk, I don't speak from my employer, and also my opinions, it's mine, and all bad jokes too. The same presentation, no, actually today presentation will be different, it's like around 40% of the content, but the title of this presentation being already presented on the USA Black Hat H2C Zero Nights and Blue Hat, and you can find by this link this presentation, but today's stuff, it's quite new. So, and my motivator being like, okay, it's documentation about the BIOS guard, and it's how Intel see for the public how technology looks like. And for me, it's like, okay, it's quite interesting because here is actually nothing, right? about implementation details. And I was actually discussed today some things about how IMEI BIOS updates working, where is the problems with current implementations, and actually why is the BIOS guard being created. And also I will discuss some interesting things about the BIOS guard, and one of the thing is inside the BIOS updates, it is like BIOS guard scripting language, which is Turing complete, and it's pretty interesting, right? Because it's actually executed by ACM model. And also I will show a few new interesting ways how to bypass Intel boot guard implementation based on American Megatrends. And also I will put a little bit more details about ACM authenticated code models. So actually pretty the same thing already been discussed by Alex Ionescu in his presentation, because operating system make much more stronger mitigations against rootkits, and actually from the firmware it's much more interesting to expose kernel or inject something inside the kernel and exploit the modern firmware. It's much more easier. And actually UEFI BIOS, it's over 6 million lines on the C code, which of course has a room for vulnerabilities, right? So, and it was pretty interesting presentation from Intel PCERT on Black Hat last year, where they discussed the bugs and different classes of the bugs, and actually the level of configuration of bugs when the vendor make it something different with specification by technology developer, and it's make a room for the vulnerability. And it's pretty much interesting, and I will show a few examples today too. And also I see some trend when some of the vendors, big cloud vendors like Google, Microsoft, and Amazon trying to make some log for the root of trust and peripheral devices by the hardware and implement their own chips. Google did Titan, and Microsoft did Olympus. And also, actually, interesting thing, because some of the root of trust moving to the cloud. And it's quite interesting, and I will actually discuss some of the new ACR models appears on Windows Server preview versions. So here is a reference if you want to grab more information about these technologies, but today I will focus on another things, but actually also about locking the root of trust in hardware and how we can break it. And but I'm actually very interested to look inside the Titan or Microsoft Olympus chip too, but it's not common to buy on the market, right? So it's no more actually legacy in the BIOS anymore, right? No legacy BIOS, and UEFI actually everywhere, and now legacy inside UEFI because different vendors have different cycles for the update their firmware, and also the ecosystem of UEFI and firmware is very inconsistent. So it's how many firmwares we have inside the BIOS update. So, and it's quite a lot, right? Here is some CV numbers. No, not here, but yeah. Oh. So one of the interesting thing, I've been looking different BIOS updates and so the BIOS update is signed, but some of these firmwares delivered separately, as example, a banded controller, and it was not. And here is the list of the files from a BIOS update, and we can see yc.bin, and I've been very interested because it's, I will not say the vendor name, but they actually don't sign embedded controller update, and also provide separate tool for update this firmware. And I looked to the tool, and it was pretty straightforward, even by the comments. So the firmware is not signed, and we can use like signed driver or signed binary with a signed driver inside, which is updates the unsigned firmware. And that's cool because like BIOS actually communicating with embedded controller some ways, and it's new room for like attacking some of the SMM services which is communicating with embedded controller from the firmware inside. And I think a lot of vendors will be look on this picture like security boundary will be not breaking, right? We already updated the firmware, and firmware should communicate in the right way with all the SMM services. Yeah. Never underestimate reverse engineering in your trod model. So, what kind of vendors today I will cover? It's Gigabyte, Asus Tech, MSI, and Lenovo, and all vulnerabilities actually there, which will be discussed today. So, it's quite high-level view how many different technologies we have to protect the BIOS, and we can see different things, and most of them it's just log bits, which is actually locking some activity from the user mode or from the kernel mode to update the BIOS. As example, BIOS log bit or BIOS write enabled. And also we do have BIOS guard and boot guard, which is actually has authenticated code models, and partially the technologies implemented in these components, and these components verified by microcode. And also spy flash protection by PRX registers, which is raise the bar for a bit more for spy flash write operations, but these three vendors doesn't use this. So, and these CVs which been discovered for Black Hat talk, and today some of the things will be without CVs. So it's the BIOS update process, and usually we have update application which is communicating with the driver, and then the driver copied the BIOS update image in specific memory and calls a watchdog over SMM service, which is actually called from the ring 0. And it can be implemented in two ways. For one of them, it's a semi-flash, and one of them, it's a security semi-flash. And actually, most interesting is security semi-flash because specifically this SMM Dixie driver verifying the signature of the BIOS update. That means it's pretty complex parser there. And also, I start looking some of the BIOSes, and they're using like SMI, SecSMI flash, but this actually dumped from one of the Dell systems where SMI flash still loaded inside SMM. So that means we can communicating with this driver because it's loaded and registered in EFI system, runtime services. So, and it was quite interesting thing because BIOS updates being checked by secure SMI flash, but we can still use this SMI flash and communicating with this SMI flash driver, and this example attacks this. So here is actually SMI handlers for security SMI flash. We can see the load image, get policy, and set policy. And get policy actually very interesting because it's the most complex parser for this driver, and it's covered the BIOS update signature verification. And I was quite interested to get in its reconstructed flow from the Dixie driver by pseudo-C, and say, okay, we have a get policy, which is pass some parameters to the function, and inside this function we have, well, memcpy, quite interesting in the parser. And actually, it was one of the main reasons why Intel creates the BIOS guard. And BIOS guard, it's actually armoring BIOS updates because all the verification flow mostly happens inside ACM model, which is actually split security boundaries between SMM and ACM. And also, all SPI flash operation controlled by ACM model. That means even if it will be vulnerability inside SMM driver, attacker can't actually raise the persistent because it's ACM communicating with the SPI flash. But of course, in the real world, that's not true because vendors want to find the ways how update firmware easier. And the technology is very complex, I mean BIOS guard, and it's hard to implement, follow all the points for specification, I think, because it's why they make some rooms for attacker. But let's discuss what Intel BIOS guard doing. So actually, first of all, it's armoring SPI flash access and access controlled by BIOS guard ACM. This partially implemented in microcode and PCH and actually using an embedded controller. And also, it's why I show some previous slide when the embedded controller not been signed. And but as example, if this platform will use the BIOS guard, but embedded controller will not sign it. It's some interesting things can be happens, right? So, and all the authentication for the BIOS updates now in ACM. But some of the vendors still have a room when we can program firmware with a physical access by flash programming tool. And also, post-update verification only rely on Intel boot guard integrity. And here is my targets for reverse engineering. Here is the list of my targets for reverse engineering. I look inside SMM drivers. I look inside ACM and also check the format of the BIOS updates because it was different. Here is the list of the components which using by BIOS guard. And actually very interesting because we can see 8 different drivers, some of them in platform initialization state, some of them on SMM and a Dixie. So it's huge attack surface because we have like 3 different SMM drivers, and BIOS guard services, it's specific model which is actually executes the BIOS guard script. So, and here's some artifacts because actually SMM drivers for the BIOS guard can be loaded, but the technology will be not enabled just because some of the developers, it's lazy to remove from the firmware image. It still appears on the platform, but not use it. So how we can know the platform is using the BIOS guard? This signature has been reconstructed, and all American Megatrends PFAT, all BIOS guard update packages have this signature, AMI PFAT, AMI BIS GD, and also if the platform using the BIOS guard, the firmware variable, BIOS guard capsule variable appears in, but actually you can't modify this firmware variable outside SMM, only SMM driver do. And also this GUID for ACM exists only when the BIOS guard really used. So how AMI BIOS guard format looks like? So we have BIOS guard header, script, and firmware update package. And also in the BIOS guard header, we can see interesting things like a firmware security version number and embedded controller security version number. And that's actually been very interesting to find that because that's mean embedded controller using by some of the services of the BIOS guard. And I start thinking about this discovery with the BIOS guard script. And when I actually found some of the comments, been conclude this language is a Turing complete language executed by ACM model, and BIOS guard services actually the SMM driver, which is pass the control to ACM with a specific command. And BIOS guard script support operations which is communicating with a spy flash chip. So here is operations which is I restore. It's load store, which is can like load and store the byte or word value, CMP, copy, jump or conditional jump, and also most interesting command and read the key hash, which is in firmware programmable fuse. It's American Megathreads BIOS guard commands. One of the most interesting is of course write and read and erase because it's using over BIOS guard update process. And these commands actually partially can be used inside the SMM driver. And it's quite interesting because it's destroying consistency of security technology, because in ideal world, it should be only ACM model which is control all the write and read operations for the spy flash. But in the real world, we have partially controlled operations from SMM driver. Here's the components and what they does for the BIOS guard. And actually, we can see for the platform initialization stage, we have capsule update validation. That's actually mean the update process, it's a bit different with previous update process, which is used SecSMI flash and SMI flash drivers, because actually platform going to some some reboot state, but it's stopped, and then platform initialization driver start not deep reboot, it's like not asleep, it's S5, and then PA driver trigger it and verifies the capsule update. It's actually make a bit fuzzy and difficult because we always don't have a feedback from the system, because if you did something wrong, it just freezes, and then after reboot you lose all the state of this fuzzing context. Also, in SMM we have a BIOS guard SMM driver, which is responsible for recoveries, firmware recovery services, and interesting thing, it has some SMI handlers, which is not communicating directly with the operating system, but it's actually have some parameters passing over CPI tables, and it's actually fuzzable. Let's discuss a bit more about ACM. And ACM, it's authenticated code model, and before I seen only ACM models developed by Intel and also signed. Actually, all ACM models signed by Intel, because verification routine inside the microcode. And ACM executes inside ACRAM. And ACRAM is specific cache state when one core will be dedicated to read, to execute inside the cache in non-invicted mode. And it's pretty much interesting because ACM model usually executed on early state booting state of the platform, but some of these SMM drivers can reload and execute during or Dixie phase too. So very interesting thing, what I find out when I reverse engineered ACM models, it's ACM models, it's mixed, developed on mixed between C and assembly language. That's pretty interesting because development teams can apply the static analysis tool, I mean like usual static analysis products for finding the vulnerabilities in the C code, but here is assembly, it destroys some the path to find vulnerabilities, and it doesn't work there. So, and actually assembly code, it's around 30% in ACM models. And okay, what kind of ACM models we have inside the BIOS update? And we do have SNIT, and currently actually SNIT and SClean is one model. It's TXT related, and Intel Boot Guard and Intel BIOS Guard. But Alex Ionescu tweeted in 2017 December about new ACM model discovered in the file system in Windows Server. And specifically this ACM related with TXT, and it's locked the secure boot state for guests inside the Hyper-V cloud. Here is a recovered format of ACM model. It's undocumented, and we can see it has an entry point and also signatures, RSA, PSS signature inside, exponent, public key, and header, and of course entry point for starting point for execution. And most of the models, it's around like 32 kilobytes to most bigger one, it was 256 kilobytes for BIOS Guard. Here is ACM header, full ACM header recovered. And actually, I will be release the model for IDA for loading ACMs before I developed only for BootGuard, but currently I made a generic model and will release after the conference. And what is an interesting thing, before it was found the vulnerabilities in ACM only in EthInit and mostly by Invisible Things labs. And we can see it was only 3 public known vulnerabilities, which is privilege escalation to ACM, but it's privilege escalation, 2 of them it's privilege escalation by code execution. So, and 2009 and 2011. And one of them actually pretty clear described inside the paper Intel TXT via EthInit hijacking. But it was no more issues found publicly. But we have, as you remember on previous slide, C and a mixed assembly code. So, and mostly all the ACM models developed by Intel use non-invicted mode and have some dependencies by chipset. So you can't take one ACM, put inside the different BIOS update for different platform and load there. So it will be not executed. And for BootGuard, it actually verifies K-manifest and Intel initial boot block, IBB. And actually I will a bit later on the next slide describe what that means. But it's a parsers, pretty complex parsers inside ACM model. So here's a flow for the Intel BootGuard, and we can see how actually many routines and code blocks we have by this graph. And here is a call graph from the entry point and what actually this ACM does. So it has a few different parsers for K-manifest, IBB manifest, and also it enables some of specific features for Intel BootGuard. And I was thinking, okay, if I take old ACM model from previous platform and make a bin diff with a new one, what I can find there, what I can discover. And it was pretty interesting because some of the flows has a lot of changes, and also actually specifically for BootGuard, I found few patches, integer overflows, and around 3 or 4 memory corruption bugs inside these parsers. So that's actually straight means like we can find the vulnerabilities inside ACM, but it's a bit difficult to exploit these vulnerabilities. But ACM models can be loaded from the file system for some of them. As you can see from screenshot of Alex Ionescu tweet, Microsoft TXT model signed by Intel loaded from the file system because it's loaded by Hyper-V. It's not loaded by Hyper-V, it's passed to SMM by Hyper-V, and then it's loaded in the invicted, non-invicted mode hash. It's pretty interesting, and it's much easier to flash from file systems. Then you have a BIOS update, you change it a bit, and then you need flash another system and boot and again make this loop. It's pretty hard and takes a lot of time. And now one of the most interesting part about new bypasses for BootGuard. So BootGuard armoring secure boot, and actually most interesting thing, it's locked root of trust inside the hardware, and been developed in 2013, but it was few the changes because when I reverse engineering different versions, I find out some of the changes in the technology. Most interesting mod, it's verified boot, where it's locked root of trust hash for vendor key inside a field programmable fuse, and there it's actually attack surface getting more complicated because we have now a hardware component. It's Intel BootGuard operating modes, but actually most interesting, and actually most of the vendors use it when they measure it boot and verified boot enabled together, and that's mean like we have root of trust located in the hardware, and also some of the paths for most software mods for sleep and for hibernate sometimes use only TP. It's the BootGuard flow when CPU actually from the reset vector before even BIOS will be enabled, start booting and getting the control. It start CPU microcode flow, which is actually execute ACM module and verify IBB initial boot block, which is usually cover sec and PA phases. Here's a chain of trust for BootGuard. So as we can see, we have some of the relations with memory engine, because memory engine responsible for programming field programmable fuse. And also we have a key manifest and initial block manifest, where is actually initial boot block stored. And also we do have a lot of different components, but for us, one of the most interesting is the signatures and what the signatures cover and the hashes values. And we can see OM root public key. And also we see this OM root public key being signed in K manifest. And it's important for the future because, remember, for the future because I will show how the vendors actually implement this flow wrongly. So it's locked by hardware, this component's inside the firmware, and what's actually validation flow doing. So it's verify by ACM security version number and execute ACM then, and after signature verification. Oh, actually it's verified boot flow from SMM. It's a bit different. Oh, actually here's interesting thing because when you close and open your lid, the vendors always fighting how fast you get some picture on your screen. And of course, if you go all the flow for verifying all the boot root of trust, chain of trust, it will be pretty long time. And they implement a specific SMM driver, which is only check the previous state of verification flow. If it is good, then it's passing control to the operating system. And it's actually the flow what this SMM driver does. And also here is a chain of trust for the OM K hash. And we can see it is we have K manifest, which is cover KMID, and we have OM key hash, which is only covered by K signature. Here is a K manifest, and also it's been recovered by reverse engineering, obviously, this SMM driver. So we can see a few interesting things. IBB manifest hash, and actually RSA signature, a public key for the components. So, and the hash, which is actually programmed inside the programmable fuse, it's there. So it's stored in this particular volume inside the BIOS update. Here is BPM, BootGuard policy manifest, and it's quite interesting because it has IBB segments, and IBB segments showing the coverage for components inside the BIOS by hashes value. And it was also recovered. And when I discovered these things, I started thinking, how I can automate to verify IBB for all different BIOS updates, because like we have all the values and this coverage pretty much easy to calculate. So I commit to BIOS guard UEFI tool for verifying boot guard values. Last year in October it was first commit, and then much more improvements in end of November. So actually attacker never attack standard, right? So it's always looking inside specific implementations, and it's pretty smart, because why we should look on the standard? Let's look how it's implemented, where is actually vulnerabilities exist. I look inside by bootguard Dixie validation flow, which is actually verifying one of the transition flag when you open the lid and return your system from the sleep. And actually, I start looking more deeply on this transition, and so error messages sometimes provide much more context for reverse engineering than other code, and these errors says like about specific verification or the state which is being in the true when the chain of trust being verified correctly. So I mean, wow, that's interesting. And after actually I showed this bug on Black Hat USA last year, Alex Yermolov from Embedded discovered the same bug inside Intel NUC and been reported to Intel, and described some details on the blog. But let's discuss more specific implementation details. It was my target platform, and it has an American Megatrends BIOS, and the same as Intel NUC use. It's why the vulnerability been the same. And actually, for the boot guard, they did almost everything properly, but they not lock it IMI because it has a read and write access, and also it's been a problem with hash because it's been not programmed. Oh, it's not been locked. It's been programmed, but not locked by field programmable fuse, and that's been quite interesting for me because we have OpenME region and programmable field fuse programmed by ME, so you can actually use a specific SMM driver to just erase this hash inside, and it will be pretty much that's it. And also, they actually use measured boot plus verified boot, which is more stronger mode, but it's not helps because of these bugs. And let's discuss how actually it's worked. So this part in hardware don't exist anymore because we already know we can clean the hash. And actually I did it in a previous presentation, show it in more details on it. And our root of trust now only firmware. So, but okay, so it's already fixed when they programmed the hash, right? So we have everything done correctly. We have disabled ME regions. We have programmed field programmable fuse. Everything is done. So what the attacker can do in this case. So, but remember, this root of trust for the key, right? And what if vendor don't verify OM key hash? And actually, I reverse engineered on Lenovo on X230 series. For ThinkPad, they doesn't verify the key hash, the vendor hash. So that means they break the root of chain of trust, but it's implemented correctly. I don't know what it was the reason, but some of the recent update being changed in last 2 weeks ago. And but previous updates, if you not update your BIOS, still have this, I don't know, vulnerability, but it looks like as a backdoor for developers. Also, for bootguard flow validation, as I mentioned, we developed a specific UEFI 2 version, and my commit actually validated all the bootguard flow, which is covered, which is not. Here is a blog post link where a bit more described about the issues and what you can find from output of new version of UEFI 2. You can actually find all information about ACM, all the keys, and actually everything, and also the coverage for initial boot block. And one of the firmwares which I recently looked don't cover everything properly, everything being covered properly. Pay, DXIF, everything. So everything covered by IBB and vendor hash. So, but it's few sections which is has a row, one volume in the pay which has a row section which is not covered. It's 3 row sections, and okay, what is inside? And they just use a bit on the beginning of this row file, and the rest of the file it just has some constant values which doesn't make sense because I changed it for check it. And okay, let's look inside how the pay driver, platform initialization drivers loader works. And okay, it's straightforward P file loader. So it's load Microsoft portable executable files. But okay, and this header, this prototype of the function you can find in Tiana core, and it's the same as implemented on American Megatrends BIOSes. And okay, it's authenticated state, so yeah, I can't do much there. But let's look, maybe it is something wrong there. I look inside the load file, and okay, here is also authenticated state. But in American Megatrends, it's always true, false, so it's never used. Because pay phase, everything loaded pretty fast. This phase should go very fast, and it's covered by, should be covered by IBB. Why we should check the signatures for all the file when it's loaded? And also specifics of loader, payloader of pay. It's just parse the firmware volumes, find the binary which has the header of Microsoft portable executable file, and start loading, because it start parse the header, discover the image size, and then start loaded. And no verification for anything there. But okay, we can actually load the pay driver, but what we can do next? So, because it will, this pay will be locked, and we actually can't do much there. Most interesting thing is getting inside the system management mode, right? And here is a path actually exists, because we have a pay driver which can discover the boot services, which is actually has a pointer to all loaded drivers by locate protocol. So boot services can easily find by the signature just in the memory or during the platform initialization phase, and then we hook locate protocol and inject malicious driver by this locate protocol function. And this structure actually exists inside UEFI specification in the header. And all the constants also there, so it's kind of unhorsed for finding inside the memory. And actually, it's very interesting because you can see clearly like implementations and the standards, it's very different, right? And sometimes you can discover very obvious bugs. Also, it's not expected being by original developers because, okay, we have a row section, but what the attacker can did there, because it's not executable file, it's just the data. But specific of the payloader allow us make something more interesting, right? And in the end, I want to say, so it's two different realities between developers and the attackers because they think in different ways, and it shows the importance to connect two different worlds in a very productive way for making products more secure, right? Thank you for your attention. And we have actually around 5 minutes for the questions.
So thank you for your lecture. I'd like to ask you to expand about the communication methods between SMM and ACM, if you could.
Okay, so the question is how SMM can use the ACM, right? Or how it's connected, because actually the execution domain for ACM and SMM is different. So SMM can be responsible only for loading ACM to the cache and specify non-invicted mode and raise some specific value for signal to CPU for execute that. And it can execute it only on the dedicated core, which is make a bit more difficult to exploit some race condition bugs.
So the SMM just loads the ACM into the cache, runs it with a...
No, actually it's signal CPU to load ACM to the cache. SMM doesn't operate directly with the cache in this way. So it's set up the mode, signal CPU, and CPU loaded, SMM mapped ACM and CPU execute ACM model inside the non-invicted mode cache. Yeah. Okay, also known as the cache as RAM. And other thing actually, the ACM is just a binary blob. The thing is, it has a signature which is validated by microcode. And yeah, so it's pretty straightforward code just in binary blob. Sometimes some very weird parsers there. And for me, it's quite surprised. It's a lot of issues been found on public because only 3 issues appears, but binary diffing with previous versions only bootguard show a lot of issues being patched silently.